to turn to page 21, please. Now, we know that the work done on an object is equal to the change in its energy. So we can say this relationship again. Okay, that the work done is equal to the change in energy. If this change in energy changes the velocity, then the work has changed the kinetic energy. If the change in energy is due to a change in height, then the work has changed the potential energy. And in a more complex system, maybe the work done changed both the kinetic energy and the potential energy. But we know that we have to conserve energy, and so we haven't destroyed or lost or gained energy, made it, created energy. We've just transformed it from one form to another. Now we can look at the change in energy, just as in the example, work example 5.1, where we want to know the work done by the brakes of a bicycle to reduce its speed from 10 meters a second to 4 meters a second. Okay, so we're interested in work, and we know that our final velocity is 4 meters a second, and our initial velocity is 10 meters a second. So our change in velocity would be 6 meters a second. Oh, no, forget that, that's wrong. We also know that the mass of the bike and the cyclist is 85 kilograms. We want the change in energy, and we can see, because we're looking at velocities, that this is going to be kinetic energy. So my change in energy will equal a half mv final, or my, doesn't matter, initial squared minus my half mv final squared. Now, you can't change this to, so this is wrong. Can't do that. It's probably the most common way that some people try and make the calculation a bit simpler, but it's incorrect. You have to keep these separate. And so now we can just substitute in, and it doesn't really matter which way around we had it. Times 85 times, but I'll just do it the same as I've got it in the booklet. If you did it this way, you'll see that you'll get a different answer. So the work done was 3,570 joules. Now, what happened to that energy? Where would that have gone?
Heat.
Heat. Yep. So brakes work with friction, so this energy would be dissipated as heat. All right, we have worked example 5.2 on the next page, which doesn't involve a calculation. It's just, again, reminding us that the pathway doesn't matter. That we can, but this is something we're familiar with in everyday life. If you walk up a ramp, then each step is easier to take than maybe climbing a ladder next to it or walking up some steep stairs. But in the end, you'll end up at the same elevation using either method, and so our work done is the same if we've ended up at the same height. we'll talk about what is actually different about it later, because we all know it's harder to climb the ladder than it is to go up the ramp, but that's not work. Okay, that's something else. And then this one is a larger example, and it's a diver. So she's diving into, she starts out up here, and this is a 10-metre platform, and then she ends up in the water. And these are very common sorts of questions. And so this is where I was saying to Aidan before, that we start to get a little bit more complicated because we combine together our potential and kinetic energy. And in actual fact, together, it's mechanical energy. It's the total of all of the energy. So because we're not thinking about friction or anything like that in this example, my total, which is written as ET in your booklets, is a sum then of the potential and the kinetic energy. Now, we start out by looking at this diver when she's at the top of the platform. So she's basically standing on at the end of the diving board. That means then that all of her energy is potential energy because she's not moving at the top there. So if I said then that mg delta h plus a half mv squared is going to be her total energy, but I know that she's got no velocity, so that's going to really knock that part out, isn't it? Tells me how much what's her mass, 50 kilos. And the height is 10 meters, and her mass is 50 kilos. Okay, so this then becomes the total energy of the system. It's not just her potential energy anymore, it's the total energy of the system. So this is what she starts with, 4,900 joules. Because energy is conserved, it doesn't matter which part of her dive we look at, we'll be able to work out her velocity, we'll be able to work out her height, etc. All right, so if we skip forward to this moment here, she's got no potential energy. So all of her potential energy has been converted to kinetic energy. So all of her mechanical energy then, like we already know, mg delta h plus a half mv squared. But now the height is 0. And so this part here comes across for energy. We can substitute in our mass. And it's going to be basically divided by 25, isn't it? The square root of that will equal V. Does that make sense? So we can determine her velocity as she hits the water, and it's 14 meters a second. Now, in the booklet we can look at, well, the way they've got it here is 5 meters into her dive. Now, I think that's a bit confusing, and probably we shouldn't do that one. I think we should do 4 meters into her dive, say. So here she's, let's say that. She's 4 meters into her dive. Okay? But our delta H is from the ground, or from the bottom. So she's going to be 6 meters from the bottom. That's what we need to calculate with. And that's why I think the 5 meters is a bad example, because it's halfway, it's not clear to you necessarily where you're measuring from. So we're interested in the height from the ground for delta H. So the energy of the system is still conserved. And we probably, what are we trying to calculate? Her velocity? Let's do that anyway. So we're still using this here. But there's going to be something for both, isn't there? 4,900 here is our total. We've got our mass times acceleration due to gravity. This time our height is 6 meters above the ground. And then we've got a half times the mass times her velocity squared. And so we can now calculate her velocity. If she is 4 meters into her dive, which means that she's 6 meters off the surface of the water. So I'm going to subtract . Multiplied by 25. And find the square root. So we can see her velocity is a lot less than her final velocity when she finishes her dive. In the booklet it does show you that her velocity is not half. She's halfway through the dive, but her velocity is not 7 meters a second. She's actually going faster because remember she started out with no velocity and she's getting faster and faster and faster as she gets closer to the water. But like I said, this part here, when we're combining them together, is a little bit more complicated than looking at them separately. I think